Hi, we are Group 10 and we are presenting our project VR Art Gallery. Uh, to give a bit of an overview, we created an application which is a VR art gallery where users get to choose from a list of preset galleries and walk around and browse through the artwork that each gallery has to offer. Users can join the gallery using either a VR headset or a desktop. The users can also interact with the canvases in the gallery. So the, the, the following kinds of canvases are available in the art gallery. The first one being a portrait canvas, which just simply displays an art on the canvas. The second one being a drawable canvas, where users get to interact with a brush and draw and create their own piece of art. The last one being the AI generated canvas, which uses Dolly to accept an audio input and display an AI generated art. Uh, the gallery also features a bunch of interactable objects such as the marker, brushes, uh, buttons, etc. the users can interact with.
Our VR art gallery supports various features such as being able to switch between galleries. When you switch between galleries, the art of the canvases gets updated to fit the gallery that you've now switched to. The art gallery has the capacity to be experienced with other users as well. This is achieved by being able to host or join a server. We have also created a drawable canvas for our more artistic visitors to create their own artwork. Visitors creating their own artwork are able to choose from a variety of brushes and a color palette with various hues and saturations. We also have a canvas for generating art from speech input in real time. All of this is supported by the ability to load and save art from the cloud using a real-time database. We have also included various graphic user interfaces for better accessibility of our features.
So, for multiplayer, we used Unity's new netcode and relay features. Netcode is their language which allows you to program network capabilities into the application that you're creating. So we used their programming interface to create a game in which you can join different lobbies using a join code, which is just a 6-digit code of characters, and you type that in the login screen, and then you can join other players' scenes. And then in each of the different scenes, all of the players' position is updated using network variables. So those network variables are transmitted to each of the different clients. And we also share the marker position and rotation. And we also share the canvas's state, so the texture on each of the canvas as they're being drawn to.
The drawing feature of our project was one of the complex computer science algorithms we implemented. A variety of brush presets were provided in a user interface to allow the user to adjust the colors, width, and height of the brush. Selecting one of the presets will automatically update the brush color, height, and width. The color palette was implemented by sampling the color of the texture at the intersection point of a VR controller or the desktop cursor. Once a color is selected and a user physically applies the brush to the canvas, it will output that color to the canvas. If there is an existing color at that position, the colors will additively blend together using weighted linear interpolation. This interpolation considers the opacity values in the final result of the color. This is important as the brush colors applied to a canvas are designed to be more transparent the further they are away from the center of the brush. The drawing is also physics-based, meaning that it considers the intersection of the brush tip with the canvas to apply a color. This has benefits such as being system independent, not relying on VR input or desktop input specifically. Linear interpolation is also performed in the drawing so that there is a smooth transition between where the user is currently drawing and where they had last drawn in the last frame. If this linear interpolation did not exist, only a series of dots would appear on the canvas instead of a neat continuous line.
We have incorporated a dedicated canvas for AI image generation within our art gallery. With this, any visitor of the art gallery will be able to speak and generate an image based on your given description. This is achieved through using OpenAI's DALL-E API, Visitors are presented with a button to record their audio input, which is generated from a simple click to toggle the recording on so that they may record themselves. Clicking the button once again will end the recording. This user audio input is then converted into a WAV file, and this WAV file then gets converted to a string of the spoken words through using the DALL-E API.
So next we take the text and we feed it into the DALL-E API, which generates an image, a JPEG image, and from that image we need to export the texture and apply it to a canvas while also using the text to update the title of the canvas. It was pretty tricky to do. We had to resolve a lot of issues, especially with the async functions. We used async functions because we didn't want the game to freeze. We had to make sure that the game was being played while we are generating the image.
So this is just a quick GIF of us switching between galleries, where you can see this image is one image appears now, and then when I change the gallery, a new image appears. So the idea was to have a list of Irish galleries that you could switch between, like Dublin City Gallery, Hugh Lane, or the National Gallery of Ireland. And when you switch between the two different galleries there, you can see different images are being pulled in. So there's about 20 canvases and about 20 images per gallery that are being pulled in. So you'll also notice that the text underneath each image is being updated to show what image, the information regarding the image being shown. So this just shows the artist's name, the title of the artwork, and the year that it was made. And these show up depending on the user's proximity to the artwork. So if you're far away, these will disappear, but as you walk up close, they'll reappear underneath the art. The only canvases that don't get affected by changing the art gallery are the drawable and DALL-E canvases, because we don't want art to change or disappear when the gallery is changed. So we're using Firebase as our cloud service provider. So we're using two different Firebase services. The first being the real-time database, which we're using to keep track of what images are in which gallery. So you can think of each gallery as being a list of images that are to be displayed when that gallery is selected. So that's what's being held in the database, so you can kind of think of it as like JSON, a JSON object, where each gallery is as an object. So what we do is, when you choose the gallery you want, we pull down all the list of names from the real-time database, and then we go and find each image in that list of names in our storage, our Firebase storage. So we go and we pull every image that's in that list of image names and apply them each to a canvas. So we were using the Spark plan for Firebase, which was a free plan for people just getting started. But after a while we used up our usage allowance, and then we had to upgrade to the Blaze plan, which is a paid plan after a certain point, which we never crossed, so it was essentially free. And all of the code managing the loading art to our canvases is in the Firebase Manager script.
The desktop version. So we've also added a desktop or PC mode, which is great because not everyone has a VR headset and they can also experience the art gallery. The desktop mode also reuses most of the code and the game objects that were used for the VR mode, and it also mimics VR drawing by using physics raycast and mouse and keyboard input. It also supports DALL-E to generate art using AI, And the desktop mode also allows two or more players to join the same art gallery at the same time, and the player can see what the other person is drawing in real time, which was a complex feature.
The art gallery features a variety of menus for both desktop and VR versions. In order to avoid creating duplicate menus, we handle the creation of menus through code so that the right menu is created for the right version, thereby making the same menu work for both desktop and VR versions. Some very specific menus were created. For example, the wrist menu was created specifically for the VR headsets to make the drawing experience more immersive for the users. A dynamic menu system was created to spawn menus during runtime, but it was later deemed unnecessary due to the performance constraints. We later realized that recreating the menus and disabling and enabling them during runtime was far more efficient than creating the menus on the fly.
Tests were created to support our development process. We quickly discovered that merge conflicts happen frequently, and utilizing unit tests to verify code is working is invaluable. This creates a fast and easy method of verifying that code works after a merge. Due to the nature of the project, not all aspects of the code can have unit tests written first, especially with multiplayer and real-time components. One such case of creating unit tests was for the drawing code and verifying that the blending of colors works. Since our color blending method used additive color blending, we can create scenarios with specific input colors and can know the exact color output. For example, if I combine red, green, and blue, the resulting color should be white. One example of unit tests not working is tracking the state of a network variable such as the position of a user. This is not possible to do in the same way as the previous case, as it relies on a runtime environment to allow the remote connection between users. Overall, unit tests are a valuable tool and should be used wherever possible.
Week period. During our first sprint, we laid the groundwork for our VR art gallery project. We focused on 3D modeling, player movement, Oculus and Unity integration, and object interactions. In our second sprint, we aimed to expand the gallery's functionality by setting up Unity Online services, exporting the project to desktop and VR apps, and creating different levels. We encountered a few technical difficulties and cross-platform compatibility issues, but were able to leverage online resources to overcome these challenges. In the third sprint, we implemented key features such as multiplayer functionality, menu design, file management, and collaborative art creation. During the fourth sprint, we focused on enhancing the user experience by refining menu operations, artwork management, and drawing tools. In the fifth sprint, we added advanced features like online communication, artwork inventory management, interactive elements, and brush control menus. And in the final sprint, we polished our project by integrating the Dolly API, adding skyboxes, adding the light to the gallery, adjusting brush sizes and colors, and allowing users to save their galleries. Throughout this 12-week project, we faced numerous challenges and learned valuable lessons. Despite, we were able to deliver a very engaging VR art gallery.
So, through the course of the days, we needed to do some code refactoring. We started by doing error handling. Basically, when we were implementing any feature, it wouldn't quite work right off the bat. So we had to implement some coding to handle the errors, debug them, to get to know what's wrong, and then resolve it as best as we could. So we built some debug blocks that we could use here and there. Next, we made sure to handle indentation and demarcation, which would allow us to group up the code and organize it better in order to be more consistent and make it more readable for future revisiting. Next, we did some modularization, which basically means that we wrapped up pieces of code that we used here and there over and over again. So repeated code parts, so we could easily use them later. And finally, we came to do the documentation, basically commenting and describing its function and its block of code in order to know what everything does when we revisit it after weeks of.
During our project, we implemented continuous integration to ensure smooth development process. This approach allowed us to maintain coherence among individual modules and resolved conflicts when merging code. We divided tasks into subtasks for easier development and integration. By adopting continuous integration, we minimized the risk of introducing errors and bugs into the software. It enabled us to catch and resolve issues early in the development process, reducing the chances of more significant problems later on. This methodology is highly scalable, making it ideal for large development teams as it can accommodate multiple developers working on the same project. It also promotes consistency by integrating and testing all code changes uniformly, simplifying issue identification and resolution, and ensuring high quality software. Additionally, we utilized merge requests subject to code review and approval from other team members, fostering collaboration and ensuring that our software met the highest standards. In conclusion, continuous integration played a crucial role in streamlining our development process and delivering a reliable, high quality product.
Problems and solutions. So we came across a few challenges during the whole process. To start with, we had to decide between the game engines Unreal and Unity. We had initially gone with Unreal because we wanted the best aesthetics for our art gallery, but then after exploring it further, we realized that it was difficult to integrate our code, and Unity was a better option since it was more lightweight and it was easier to add our own components along with the game engine. And another big issue that we faced was admin privileges, which meant we had trouble running the project on the lab computers, and we spent a lot of time trying to get those permissions. Another big issue was the TCD Wi-Fi, because when we were testing out the multiplayer functionality, we thought it was broken, but then it was using the TCD Wi-Fi and it only worked when you switched to your mobile hotspot, and we realized that a bit late, and a significant amount of time was lost on that.
So I thought I'd just go over a few things that we took into consideration while designing the gallery and the map that it's in. So first of all, we designed the layout of the map from scratch. We wanted a nice demo area that showcased a few of the different features that we'd planned for our app. So we have the reception area, which has the menu. We have the hallway which has a bunch of the artwork displayed. And then we have the 3D model area down the back, which has some of the statues that we wanted to experiment with as well. And then the main area in the middle, which has our DALL-E canvas and our drawable canvas and some more artwork as well. And then some of the other considerations that we took into account were optimizing the models for VR. So we found a lot of nice furniture models and everything, but we needed to take some time to compress the models, make sure that the UVs were correctly set up so that we could create light maps and bake the lighting so that it could be optimized for VR as opposed to just using real-time lighting. We placed reflection probes around the scene so that real-time reflection would work. and we used a nice cube map to light the scene, which gave us the realistic looking sky above head, and you can see it's down here in the image below.
We will now show the various features implemented in the art gallery. The first is the ability to switch and load different images from various art gallery presets. This will populate the entire gallery with those specific images to that preset. Our integration with the DALL-E API has allowed us to generate AI images in real time based on the user's audio input. Drawing takes place using physics-based interaction with the brush and the canvas. The canvas will be updated based on the various attributes set on the brush by the user wrist menu. The user can update the color chosen and apply it to the screen, as well as the other attributes. Color blending also occurs here in the system.
Here we can see the desktop version of our art gallery. You can host an online game. Note that all of the artworks on the walls are currently blank. If we change the gallery that we are in, this change will be reflected in the artwork. When you walk up to an artwork, you also get information of that artwork, such as the name and the time that it was created. The desktop version for the art gallery also has support for drawing on a canvas. You are able to choose from a color palette to change the color of the marker being used to draw with. As you can see, there are other options such as changing the width and height of the marker. There are several brushes that you can use, such as a pencil, which has very thin lines, or a marker which has thicker lines. Also note that color blending is happening here. The desktop version also has support for generating AI art. Speaking into the record button will save the input as a WAV file, which is then translated into a text file, which is then used to call the DALL-E API to generate this artwork. In this case, the user prompt was a bunch of seagulls playing the guitar.
We will now demonstrate multiplayer happening across multiple desktop clients. The state of both clients is able to track both the position of each player as well as the position of the brush in the game. This allows both the players to be able to see and interact with the drawing canvas.